Now we're taking a look at how to write the formula for an ionic compound. An ionic compound has to have some sort of ion in it. Most times you'll have a metal with a nonmetal. The first part will have a positive charge and the second part will have a negative charge. And it's easy to find these things on the periodic table. The metals, as you may recall, are on the left-hand side, to the left of the staircase right here. These are all the metals. And the nonmetals are the ones that are to the top right. So with our formula that we saw here, we'll have the metal or something on the left side of the periodic table first, followed by the nonmetal, something from the right-hand side. So that should give you some guidance as to where you should be looking on the periodic table when you're trying to write these things. Also, you could have something known as a polyatomic ion. And all a polyatomic ion is one of these guys right here on this list. Okay. These are groups of elements that are bonded together that have an overall charge. You can see that everything right here is a -1. These are all -2s, 3s, 4s, and there is a +1 ion. Okay. These things substitute for the metal or the nonmetal. Okay. And things you look for a polyatomic ion, things that end in ATE or ite. Things that end in ate or ite are going to be things that are found on your polyatomic ion list. Okay. So it's the best just to go ahead and start working through some of these so you can see. So what we're looking for is what charge do each of the terms have, the first one and the second one, and then what ratio do we have to write these in. So if I find potassium, potassium is an element. It's on the periodic table. We can find that right here. It's element number 19. And if we look to the top right here, I have the oxidation states for each element. So you can always tell for these groups right here what charge ion they're going to make. Things in group 1 make a +1, things in group 2 make a +2. We have a +3, +4 because these are all trying to lose the electrons, which would give them a positive charge. And the nonmetals to the right here, these guys are trying to gain extra electrons, so they become negative. So -3, nitrogen has 5 electrons looking for 3, -2, -1, and the noble gases don't form any bonds, so 0 charge there. Okay. So we found potassium. We saw that it was a +1. So we just write that on top of the word potassium. Iodide. Okay, well, this thing ends in IDE. We know that things that end in ATE and ITE, ate and ite, generally are on the polyatomic ion list, but things that end in ide are going to be things on the periodic table. So the word was iodide. So what word in the nonmetal region is going to have an ide at the beginning, an iode, and it's iodine. So iodine we can see is in the -1 group. So we write a -1. And the whole goal of this is to have the positive side balance the negative side. So since I have a +1 here and a -1 here, those equal each other out. So it's just simply a matter of writing out the symbol for each. 1 K and 1 I for 1 potassium and 1 iodine. That's the formula for potassium iodide. Okay. This time let's take a look at sodium carbonate. Well, sodium, we can go ahead and take a look on the periodic table. Sodium is a +1, but carbonate ends in ate, and if we recall, we said that things that end in ate are usually on this polyatomic ion list. So we take a look there. Okay. And we're looking for carbonate. Here it is. We see that carbonate is a -2. Okay. So the +1 and the -2 do not equal each other out. So what we do in this case is something called the criss-cross method. All we do is we take the oxidation state for the positive ion and we're going to write it as a subscript behind the negative ion. And we're going to take the other one and write it this way. So Sodium was Na, and we bring the 2 that we wrote above the negative ion carbonate down as a subscript for sodium. And we have a 1 that's coming down to go behind carbonate, but we don't write 1s. They're understood. In the first problem, they were both 1s. We didn't write 1s. You understand a 1 as being there. So you just need to write the formula for carbonate now. Carbonate was a CO3. Ignore this negative 2 when you're writing out the formula. This was just to tell you what the oxidation state was, what the charge is. This is not going to be part of your formula. You will not write the negative 2. There's no negative atoms, so it's just the CO3. The 1 got brought down, and we don't write that. So Na2CO3 is sodium carbonate. Okay, a little faster now. Barium acetate. If you look on your periodic table, we know it's on the left-hand side, and you'll find it in group 2. That is a positive 2. Acetate ends in ATE, so that is going to be something from your polyatomic ion list right here. We find acetate under the -1. It's C2H3O2. So it was a -1. We're going to crisscross these. Barium, Ba. We don't write the 1, it's understood. Now we have acetate, which is C2H3O2. And we need to put this 2 on it. Well, I can't just stick a 2 at the end of it. The way that we write a subscript when we have a polyatomic ion is we have to put it in parentheses. Now I can put the 2 behind it. Lead to nitrate. Okay, things that are in the middle region of the periodic table. See, we didn't write the oxidation states for any of these right here because they can vary. They can have several different oxidation states. Unlike a lot of these guys just have the 1 on top. These can have multiple ones. So we show what the oxidation state is by using Roman numerals. So because this is lead to nitrate, that 2 part of it tells you that lead is a positive 2 ion. Nitrate, ATE, going to be on your polyatomic ion list. We find it. It's NO3 and it's a -1. So now we just crisscross. Lead is Pb. It gets the 1, which we don't write. NO3 for nitrate, it's going to get a 2, so we know we need it in parentheses. Finally, tin 2 oxide. Same as above. It's one that has multiple oxidation states, so if it tells you that it has a certain oxidation state, you always use the number in Roman numerals. So that's a +2. Oxide ends in IDE, so things that are end in "ide" generally are on your periodic table. So oxide, the root of that is ox right here, so it's going to be oxygen, which is a -2. Okay. Now we've been crisscrossing because they were different oxidation states, but as we can see here, +2 and -2 cancel each other out. Okay, this is already a neutral compound, so we don't need to write any subscripts. All we have to do in this case is just write out the symbols for each. 1 tin will balance out 1 oxygen. Just SNO is the formula for tin oxide.